Hi, my name is Markel and I'll be presenting our work studying the impact of batch deep reinforcement learning on student performance. A simple act of explanation can go a long way. So let me start by introducing reinforcement learning. Reinforcement learning has been able to successfully solve simple tasks such as the mountain car, grid world navigation, or the card ball. In recent years, deep reinforcement learning has been very successful in more complex tasks, such as the game of Go, in some physics simulators, and in robotic tasks. Deep reinforcement learning combines traditional reinforcement learning algorithms with neural networks, which provide a very powerful function approximation tool. Reinforcement learning has also been used in educational domains. Chi and others applied policy iteration to maximize learning gain. A partially observable Markov decision process framework was also used to achieve faster student learning by Mandel and others. Shen and others, who investigated the effectiveness of immediate and delayed rewards on the policies used in educational systems, concluded that immediate rewards were more effective at improving student learning. Other papers have also applied deep RL or hierarchical RL techniques to improve student learning in intelligent tutoring systems. Intelligent tutoring systems are computer programs that provide one-on-one interactions with students. They also provide customized and individualized learning and step-by-step solutions to the problems, while making adaptive hints and feedback available. To provide all these things, the intelligent tutoring system needs to decide how to provide the adaptive instructional intervention. So the pedagogical policy is about deciding which instructional intervention is optimal for improving the student's learning process. Recently, reinforcement learning has been used to learn pedagogical policies for intelligent tutoring systems directly from student-tutor interaction datasets. However, we need to make a distinction between agent-centric reinforcement learning and human-centric reinforcement learning. In standard reinforcement learning, an agent learns how to interact with the environment to maximize long-term rewards. At any given time point, the agent observes the environment in a state, it will take an action and receive a reward, and then observe the environment transitioning to the next state. The goal of reinforcement learning here is to make the agent smarter. We refer to such reinforcement learning process as agent-centric reinforcement learning, which differs from our work, which can be referred to as human-centric reinforcement learning. In human-centric RL, the human will interact with the environment, and the goal of the agent is to make the interactions between the human and the environment productive. At any given time step, the agent observes how the human interacts with the environment, takes an action, gets a reward, which is a result of the interaction between the human and the environment. Different from agent-centric reinforcement learning, there are two agents involved, the human agent and the reinforcement learning agent. Many real-world tasks are human-centric, such as healthcare, where the goal of the AI is to make patients healthy, or in education, which is the focus of our work, and the goal is to use AI to improve student learning outcomes. Often, when dealing with human-centric tasks, we need to train the reinforcement learning algorithms offline, which is also known as batch reinforcement learning. That is, the agent will learn a policy from existing datasets. This is because 1. There are no accurate simulations available, or 2. It is not ethical or legal to explore the environment while training the policy. One common issue in human-centric reinforcement learning is that collecting data is often expensive. For example, it took us 6 years to have the training data we used for this work. Generally speaking, when applying reinforcement learning to human-centric tasks, we face many challenges, and in this work we focus on 2 of them. In order to improve human-centric reinforcement learning systems, we identified 2 issues, agency and communication. In most human-centric systems, the agent does not communicate its decision with the humans. However, in education, students often learn better when they are aware of what is happening inside the system. And second, since human-centric reinforcement learning involves 2 agents interacting with one another, there are 2 different agencies, the student agency and the ITS agency. Students often prefer to make their own decisions rather than following a predefined policy, since they might know better than anyone what their educational needs are. In this work, we define two hypotheses to tackle these issues. First, the communication hypothesis. We state that an RL-based policy combined with improved communication through simple explanations would outperform an expert design policy. Second, in the agency hypothesis, we state that letting students make their own pedagogical decisions can be more effective than using an expert design policy. For our deep reinforcement learning-based policy, we use the DQN algorithm, with an improved version named double DQN, where the agent will learn the Q value of every state using the Bellman equation, and it will learn to choose the action with the highest expected sum of cumulative rewards. We also used a method called InferGP to infer the immediate rewards from the delayed rewards in our system using Gaussian processes. This helps mitigate the credit assignment problem in reinforcement learning, and it improves the learning of the agent. We combined DQN with InferGP and used it to learn a pedagogical policy in our intelligent tutoring system directly from a dataset of past student-tutor interactions. Our ITS is named DeepThought, and it is a graph-based logic tutor used at North Carolina State University for the discrete mathematics course. The user interface is shown on the right. DeepThought uses 142 features to represent the state, which encapsulate the behavior of the students. There are 10 autonomy features, 29 temporal features, 35 problem-solving features, 57 performance features, and 11 hint-related features. From each state, DeepThought needs to provide an action, which can be either problem-solving or word example, also known as PS and WE. This image shows the user interface of DeepThought when a worked example is shown. The user can click through the example and the different nodes needed to solve the problem appear on the graph, as shown on the left side of the image. On the right, the interface shows explanations related to what rule is being applied at each step, until the problem is solved. And this is the user interface of DeepThought in the case of a problem solving. The problem must be solved by the student using the rules and principles shown in the middle column, which can be applied to the nodes shown on the left side until the conclusion node is reached and the problem is solved. We use this ITS with classroom students to design two different empirical experiments. In both experiments, students go through a standard pre-test phase, followed by training on the ITS and ending with a post-test. For the first experiment, carried out in fall of 2018, we split students into two different groups, a DQN policy with 41 students in it and an expert policy with 43 students in it. We use this experiment to measure the impact of only using DQN without any explanations and compare it to an expert baseline policy. For experiment number 2, which was carried out in spring of 2019, we split the students into 3 groups, a DQN plus explanation group with 30 students in it, an expert baseline policy with 23 students in it, and a student choice policy with 30 students in it. Experiment 2 is where we will test our agency and communication hypotheses by comparing the DQN plus explanation group against the expert group for the communication hypothesis and comparing the student choice group against the expert group for the agency hypothesis. Let's begin with experiment number 1. We compare the pre-test and the post-test scores the students obtained in the DQN group against the scores obtained by the students in the expert group. A one-way ANOVA test using the group as a factor showed no significant difference on the pre-test scores between the two groups, so the groups were balanced in their incoming competence. A one-way ANCOVA test using the pre-test score as a covariate and the group as a factor also showed no significant difference on the post-test score. We also performed a log analysis on both groups to determine whether the two policies behaved differently during the training stage of the ITS. We analyzed the total training time, the number of PS problems, the number of WE problems, and the number of hints requested by the students. We observed no significant differences in any of these categories during experiment 1. We only observed a marginal difference in the problem-solving count between the two groups. Therefore, we conclude that in experiment 1, the DQM policy did not outperform the expert baseline, so the DQM policy is not better than an expert design policy. And the two policies don't show significant differences in the training time, problem-solving count, word example count, and hint counts. Next, we will show the results of experiment 2, where we tested our communication and agency hypotheses. In experiment 2, we compared the pre-test and post-test scores the students obtained in the DQM plus explanation group against the scores obtained by the students in the expert and student choice groups. A one-way ANOVA test using the group as a factor showed no significant differences in the pre-test scores among the three groups, so the three groups were balanced in their incoming competence. A one-way ANCOVA test using the pre-test score as a covariate and the group as a factor showed a significant difference among the three groups on the post-test score, and subsequent pairwise ANCOVA tests found a significant difference between the DQM plus explanation group and the expert group, so the DQM plus explanation group outperformed the expert group in the post-test. We also performed a log analysis on the three groups. A one-way ANOVA test showed no significant difference in neither the training time nor the hint count for the three policies. However, a marginal difference was found in the number of PS problems, and a significant difference was found in the number of WE problems. DQM provided fewer WE problems than the other two policies. Furthermore, we performed a correlation analysis to study the correlation between different metrics and the post-test score. When analyzing the correlation between the training time and the post-test score, we found no significant correlation. When repeating the same analysis between the PS count and the post-test score, we also found no significant correlation. However, we did find a significant correlation between the number of WE problems and the post-test scores when combining all the students. But when splitting the three groups together, we only found a significant correlation in the DQM plus explanation group and not the rest. And finally, we found no significant correlation between the hint count and the post-test score. In summary, it seems like there is some negative correlation between the number of WEs and the post-test score, but these results might not be meaningful since that was only observed in one of the three student groups. In summary, we conclude that our results confirm the communication hypothesis since DQM plus explanation outperformed the expert policy in experiment 2. However, we could not confirm the agency hypothesis, since no significant difference was found between the student choice and the expert groups in terms of post-test scores. Finally, our log and correlation analysis suggests the students might not know which type of intervention is best for them. And that could be the cause why student choice group did not outperform the expert group, but more investigation is necessary in this matter. In general, we explored a way to combine deep reinforcement learning-based pedagogical policies with better communication strategies using simple explanations. We also evaluated the impact of student decision-making on their learning process. And our results show that the DQM plus explanations policy can outperform the expert design pedagogical policy, confirming our communication hypothesis. Thank you very much.